Okay, so let's do some more example problems concerning Sn2 reactions now that we've talked a little bit about other factors that affect the reactivity of these organic molecules and the nucleophiles themselves. So let's look at the first example, and it says which is a better nucleophile. So this is how it would be presented on a test or a homework question, and we've got four parts to the question: A, B, C, and D. So which is a better nucleophile? And let's take a look at A first. And it says, is bromo a better nucleophile or is chloro a better nucleophile? So we have to make sure that we're on the same page when we take a look at nucleophile. Which one is the better nucleophile? This AKA means pretty. Which one is prettier? Meaning, which one of these two choices would go in and have a better time replacing a group on an organic? That is what we mean when we say better nucleophile. Which one can actually replace easier? So for instance, if we had an organic and we have maybe the worst nucleophile on the organic, which is iodine. Iodine is the ugliest group on there. Would bromo be a prettier choice, or would chloro be a prettier choice when it concerns the nucleophile going in and replacing it? So, in other words, if this carbon had to choose between two people, would it choose bromo or would it choose chloro to replace the iodine with? Okay, so that's just an example. I like to use iodine because it's typically at the bottom of the list, meaning the ugliest nucleophile out of all of them. And really anything should be able to go in and replace poor ugly iodine. So the question is bromo or is chloro a little bit better? So here is the table yet again. And this table, if we look, has the iodine up at the top. So we know that's the ugliest. And then here's bromine right below it. And then here's chlorine below it. So we always said that the prettiest nucleophiles are down below. So down here at the very bottom, that is where we see our NH2 group. And we said our NH2 group is Miss America of the bunch. So this is the prettiest, meaning it will replace anything else above it. So if I look at my choices between bromo and chloro, chloro is further down the list. That means it's prettier than the bromo group. And if it's prettier than the bromo group, then that means that my chloro is a better nucleophile. So that means that if bromine is on this molecule, chlorine is actually pretty enough to come in and kick the bromo to the curb and take bromo's spot. If I take a look at B, we have CH3O minus and CH3OH. Notice that the difference here is just a hydrogen. And one of these has a charge and the other one does not. This one is neutral. Okay, so I don't need a chart for this one. This one should be very easy. Which one is the better nucleophile? Nucleophile, remember, means neutral loving. Which one of these would want to have a neutral charge the most? Well, if I look, my CH3O minus has a negative charge. My CH3OH is neutral already, so I don't need to use the nucleophile chart for this. I know, just based on charge alone, that this would be a better nucleophile because this one wants neutrality a little bit more. So it's carrying a negative charge. That negative charge is what makes it a nucleophile versus something that's protonated like this one. Okay, if I take a look at C, OH minus or NH2, well, this one should be very easy as well. I should not need a chart for this one either. We said that NH2 is Miss America of the bunch. It will replace anything at all. And if I look on the chart, NH2 is down here at the very bottom, and OH is above above it. So that means NH2 is prettier, and it will replace anything else that's above it. So for that reason, NH2 is going to be a better nucleophile. If I take a look at D, here we have two choices. These choices we might be unfamiliar with. This one is really coming from a carboxylic acid. So this was a carboxylic acid. We don't know too much about that yet. We've not talked about the reactions of carboxylic acids, but we will in the future. And then this SH is called a thiol. So it's kind of like OH for alcohol. And what we do is that we keep the OL ending, and the thio means sulfur. So this is a thiol group and what was a carboxylic acid group. Okay, so we need to know which one of these is prettier. So I go to the chart, and here's the chart. And here is the CO minus double bond O with a CH3 group. It just so happened to be the same exact thing, but please be forewarned. It doesn't have to be exactly the same. That can be any R group that it needs to be. So this could actually be a CH2CH3 group. I'll look at this piece here, the piece that carries the negative charge. This is a negative OC double bond O. That is what's the most important. So I still would go to that if this alkyl group was a little bit different. So here's my CO double bond O, and then right below it is my SH, my thiol group. So SH is further down the chart, which means it's prettier. It will replace anything else above, and that means that this would be my better nucleophile out of the two choices. So that's how you would answer those questions when they would come around. Just use your chart, understand what the chart means, and you'll be able to use it for the homework, of course, and it will also be on the test. So you don't have to memorize them, not yet at least. All right, so let's take a look at example number 2, and this says which reaction occurs the fastest. So here we have a reaction for A, and here we have a reaction for B, and we want to know out of these two choices which one would go forward the quickest. So again, we're really looking at nucleophiles and how pretty they are. And so if I take a look, this organic is the same as this one. There's no difference. This is ethyl bromide and this is ethyl bromide. So out of my two choices, what's changing is the water and the OH minus. So I have to question, in this case, which one is the better nucleophile, because that will drive the reaction quicker. Well, again, nucleophile means it needs to be neutral. This carries a negative charge, the other one does not. So this reaction choice would happen faster because of that. If I take a look at B, well, this time they're keeping my nucleophile the same, my OH minus and OH minus. What they're changing on me is the organic that's here, this alkyl halide. And here they've put a methyl group a little further away from the bromo, and here they've put an alkyl group closer to the bromo. And I need to figure out which one would happen quicker. Well, again, this is all about sterics. Okay, so how many buddies is bromine bringing to the party? Well, this bromo group, if I look at this carbon that's attached to the bromo group is a secondary carbon. Over here with this alkyl group, the bromo that's attached to the carbon, that carbon is attached to only one other. So that's a primary carbon. And if I go back and review the rules of Sn2 reactions, I know that primaries happen much easier than secondaries, and we've explained why now. And that's the reason, because bromo is not bringing friends to the party. So there's nothing really covering up this carbon except for these down here way below. And this bromo group brought a methyl friend to the party, and that's kind of helping take up for the bromo group and blocking this OH from coming in. So steric hindrance is at play here. So out of these two choices, this one happens much quicker. And then down below for part C, I see the same alkyl halide here and here. So what they're doing is they're changing the nucleophile on me. OCH3 or the SCH3. So the question is, which one is prettier? If I go and take a look at my nucleophile chart, here is my OCH3. Again, it's kind of like before. This is an alkyl group. It can be any alkyl group that it wants. It doesn't matter. This is an OR group. Just so happens it matches. And then my other choice was this SCH3. So here's the OCH3, and then here's the SCH3. Again, they just put ethyl here, but it can be any alkyl group it needs to be. So OCH3 is further down the chart, which means that this reaction is going to happen quicker.